All right, this is our first lesson of our independent unit on matrices, and it's an introduction to matrices. We're going to do some work with some of the notation and terminology that you always have to look at when you're introduced to something new, and some of the basic operations that you can do with matrices. Now, a lot of this lesson is self-explanatory. It's designed to be that way, so I would say go ahead and read through it yourself before we go through it together. Some of it doesn't really require an explanation, so I'll quickly try to point out some of the important details. There is one part, however, of working with matrices that is a little bit trickier, and that part we'll spend a bit more time on. Okay, so I would recommend pausing the video now and going and reading over this worksheet before we start working on it together, because like I said, a lot of it's self-explanatory, and it'll be good if you have read through some of it. That being said, we'll go ahead and get started. So first of all, the definition of what a matrix is. A matrix, and we plural matrices, is a rectangular array of numbers that are arranged in rows and columns. So we've got 4 different examples here, and you can see they're all different sizes, and we'll talk a little bit about their size and more momentarily. So each number appearing in an array we refer to either as an element or an entry of the matrix, and depending on their size, obviously they have more or fewer entries. The dimensions of a matrix. This is important. This matrix from above has 2 rows and 2 columns, so we say its dimensions are 2 by 2. Now this one has 2 rows and 3 columns, 1, 2, 3. So the rows are going across and the columns are going down vertically. And so it has 2 rows and 3 columns, so its dimensions are 2 by 3, which is very important that rows come first. It's always rows by columns. And I hope it's obvious that you cannot change that. That's a pretty strict convention, and that's the way that we talk about them. So you have to know that rows come first. The matrix, this matrix has only 1 row and 4 columns, so its dimensions are 1 by 4. And this one's a bit silly because we don't usually see matrices this big, but it has 7 rows and 5 columns, so its dimensions would be 7 by 5. Okay, dimensions are important. Different operations can happen because of the dimensions of a matrix. We talk about the dimensions of a matrix in terms of what it represents. So it's kind of a big deal, the dimensions and the size of a matrix. And this is just a summary. In general, M by N is a matrix with M rows and N columns. Rows always comes first. Okay, and these are called the dimensions of the matrix. Now, if I have matrix capital A, then the entries would be referred to with small a's, and this is not an 11. It's the first row in the first column, first row, second column, first row, third column, first row, nth column, and these are obviously all second row, and this is the mth row, first column, mth row, second column, and so on, mth row, nth column. Okay, so we can refer to each individual element and its location in a particular matrix with this notation, and it's called the ijth entry, and again, rows always come first. Okay, so that's a way that we can refer to a particular entry. Sometimes if we have a matrix with 1 row, it's called a row vector, and sometimes if we have a matrix with 1 column, it's called a column vector. And it makes sense because you will notice a lot of overlap between matrices and vectors, and if you explored more linear algebra, you would find that matrices and vectors are used together, and a lot of the things about them are the same. And all of the stuff that's interesting, because the stuff that you've learned about vectors, dot product, cross product, has applications in matrices as well, but it sometimes looks a little bit different because matrices can be different sizes. Okay, so if we're comparing matrices, most of this is going to be very intuitive. 2 matrices are the same size if they have the same dimensions. Easy enough. Then 2 matrices are equal if and only if their size obviously has to be the same and all their corresponding elements are equal. So if I have A and B, then Aij will equal Bij for each I and j for the entire matrix. And if that's true, then A will equal B. Zero matrix can be any size and all the entries are 0. So there's a 2 by 2, zeros everywhere, 2 by 3, zeros everywhere, similar to the 0 vector. And again, if you did we haven't talked about it yet. We're going to momentarily. If you had two equal matrices, so you did something like A minus A, you would get the 0 vector. That's the same size as A. Okay. The identity matrix. Now, a lot of this stuff we're not really going to get into too much. We're not going to use these very much, but this is all fundamental stuff for matrices. And the identity matrix is a very big one. We won't get to see how important it is, but it is a very, very important matrix and concept. Okay, so first of all, it must be a square, which means equal number of rows and columns, and all the entries are 0 except the diagonal is shown. Starts in the top left, goes to the bottom right every single time. Okay, and they're all ones down that diagonal, and everything else is 0. And that's the identity matrix. And you can almost think of it as like the number 1 when you're working with numbers. It's not obviously exactly the same, but it can be, sometimes it's along those lines. And we think of how we multiply by 1 conveniently very often when we're simplifying an expression. And so the identity matrix sometimes pops up like that as well. So here's a 2 by 2, 3 by 3, 4 by 4. So that's important to know for future. Unfortunately, we won't really get to see it very much. Matrix addition. This one's, again, intuitive. If they're the same size, you get their sum by just adding corresponding entries. So take a look, 4 plus -2, which gives you 2. And those came from the first row, first column, and the result goes in the first row and first column. So 11 and 12 gives you 11 plus 12, which is 23. Second row, second column, second row, second column, second row, second column. And we'll do one more. 2 plus 9 is 11. Third row, first column, third row, first column, third row, first column. Okay, and that is how you add matrices. So and that you would subtract them the same way you would subtract each entry. So that means, though, that the sum of these doesn't exist because they're not the same size. So you can't add them. They don't have corresponding entries. There's no way to add those. And I'll let you look over the properties of matrix addition on your own. This one we'll talk about momentarily, but this, obviously, if you were doing more of this kind of stuff, this would be important. This is kind of what I was talking about before. If you have -a and -a and you add them together, you would get a 0 matrix of the size of A. Scalar multiplication, we recognize that. That sounds familiar, and it is exactly like it is with vectors. So if I'm multiplying any matrix by a scalar k like we're doing down here, then their product will be the same size as A, but every entry is multiplied by A. So -5 times -2 gives you +10. Multiply by the first row, first column, entry goes in the first row, first column. 5 times 7 is -35. -5 times 7 is -35. Okay, so again, very intuitive. 2a will be the same as a plus a. That's familiar in terms of how it would work with numbers. So there are lots of details with matrices that are the same and intuitive in a way because it's similar to what we've always done. And that's good to know. But not everything with matrices is like that, just like not everything with vectors was like that. Again, I'll let you look at the properties of scalar multiplication on your own. Good to know if you were going further with this. Now, matrix multiplication is the one we're going to spend a little bit more time on because it is a little bit more tricky. First of all, kind of similar to summing matrices, not all multiplications will be possible because in order to multiply matrix A and B, this is what's important, the number of columns of A must equal the number of rows of B. So let's take a look. I have 1, 2, 3 columns and 1, 2, 3 rows. So these two can be multiplied together in this order only. Also, order matters. If I change the order, then it would not work because then the columns would not equal the rows. Okay. They each have 3, so we can do it. So let's take a look and dive into this and see what it actually looks like. The reason why you need the same number of columns in the first one as rows in the second one is because I multiply each element in the first row by the corresponding element in the first column. And so I do 1 times 7, which is 1, and let me do this again and color code it. 1 times 7, which is 1 times 7. 3 times 5 is 3 times 5. And 11 times 0, which is 11 times 0, and then I add them together. And this looks familiar too. It kind of looks like the dot product, doesn't it? And that's not exactly an accident. Again, we won't get into that too much, but so I multiply the first, the second, and the third, but going across the row and down the column, and then I add them together. So what is that? 1 times 7 is 7, plus 15 plus 0 works out to 22. Okay. So that was the first row, first row with the first column. Now we're going to do the second column. Okay, so I get 1 times 8 plus 3 times 0 plus 11 times 2. So that works out to 8 plus 22, which is 30. So this gave us that second one. Okay, then we move on to the next column and we just do all the columns in order, and the first column, the result goes in the first column, and from the first row goes in the first row, and this was the first row and the third column that we're going to do now, so it's going to be in the first row and the third column. So you can kind of see how this starts to line up. So 1 times 0 plus 3 times 2 plus 11 times 1. So that looks like 6 plus 11, and this will go here. Whoops. And that looks like it should be 17. Okay, and the next one, I won't write down this whole one. So it's 1 times 6 plus 3 times 7, 21, plus 11 times 9. So that's 99 plus 27, which is 126. Okay, and then I'm done with those, and what do? I move on to row 2 and go back to column 1, and I repeat the process. So this is 14 minus 20, which is negative 6. Next one, this is 16 and 0, and 16 plus 12, which is 28. Next one is 0 minus 8 plus 6, so negative 2, and I will write out the last one again. It gives you 2 times 6 plus negative 4 times 7 plus 6 times 9, and that one's a little bit bigger, but I believe it works out to 38. Okay, so that's how you do matrix multiplication. So that one is not intuitive. And this is one that will require some practice and some focus and some understanding and some remembering of exactly how this works and how the dimensions come into play. Now this is a summary of the process, but it's an important one, okay? So it says that, in order to, let me do this again. In order to multiply two matrices that have particular dimensions, so A is P by R and B is S by T, the number of columns of A must equal the number of rows of B. In other words, R must equal S. And if that is true, the resulting matrix will have dimensions P by T, because the number of rows I had here gave me the number of rows I have here, and the number of columns I had here gave me the number of columns I had here. So you can see that there's real importance in how the dimensions interact with matrix multiplication. And again, that's something that you want to know. Now, if you can get this algorithm down, you don't have to memorize this. You can kind of just figure it out. It just makes sense. Again, there's the properties of matrix multiplication. I'll let you go over those. Again, would be important to know if we were getting into this more, but we won't see too much of that. Now, the final thing we're going to talk about is the transpose of a matrix. And it is written out like this. It looks like A to the exponent T, and that's just how we refer to it. So if A is this 4 by 3 matrix, then the transpose of A will be a 3 by 4 matrix. And in fact, if some other matrix B was M by N, then B transposed would be N by M. And not only that, but if you look, the first row was 1, 2, 3, so the first column becomes 1, 2, 3. Second row, 4, 5, 6. Second column becomes 4, 5, 6. And that is another thing that is used in some types of math where we use matrices, but it's probably not something that we're going to see very much. But it is a definition that you need to know. And that's it for the introduction to matrices. So some of the operations, like I said, and a lot of the terminology, it is similar to vectors, but there is some stuff that's new there. And definitely the multiplication requires some practice just to make sure that you have it down. Okay, so there's some practice that you can do, and good luck.